Alright, in this video we are going to be going over Dijkstra's algorithm, and this is a part 1 of 2. It's going to take us 2 videos to completely go through the algorithm. So before we get started, I thought we could highlight the person who came up with the algorithm, Edgar Dijkstra. He is very influential in the field of computer science for many different things, and I thought we could talk a little bit about him. He's one of the first scientists to call himself a programmer, and he was doing this work in the 1950s, and so he really got into computing through his training in theoretical physics. So he got really interested in computing through the use of them to, study physics, but really became a computer scientist. He contributed to the areas of compilers, operating systems, concurrent programming, software engineering, programming languages, algorithm design, and he also was a teacher in all of these areas. Some of these areas that I've highlighted here, there's very specific things that he came up with and that are still used today. One of those is Dijkstra's algorithm within algorithm design. So it's really hard to pin down what he is most famous for because he's contributed so much. One of the kind of fun things that he did is he once wrote a paper about how harmful it is to use goto. So it is a statement that exists in C++, but it's rarely ever used, if ever. Other fun things, his name has the letters IJK in it, and I think it's really cool how that also is the first 3 indexes we use for loops, particularly in physical modeling when we often have loops in 3D space for all 3 dimensions. IJK is the standard notation for that. He also had really beautiful handwriting and wrote his early papers, hand wrote them, which is unusual, and the font that's used on these slides is representation of his handwriting. So the problem that Dijkstra's algorithm is solving is a shorted weighted path problem. It's known as a couple different things: shorted weighted path, shortest distance, shortest path. It generally solves the shortest weighted path between 2 nodes, but it can also solve the shortest path, which would be like an unweighted graph and just the least number of edges. So we're going to talk about this in terms of an algorithm you're already familiar with, breadth first search, and kind of motivate it with the algorithm in breadth first search. So if you wanted to find the shortest weighted path between G and F, you could use a modified version of breadth first search. So you'd start at the starting vertex, which would be G in this case, and you would keep track of your distances. So roughly the idea of this algorithm is something like this. So you kind of have this queue that you keep track of in the algorithm anyway, and while you're walking through the algorithm, you're going to keep track of the distances along the way. So to start off, we'll just say that the distance is 0 because we're at the node that we started at. And then we'll just go ahead and visit all of the neighbors of the node that you're at. So I'm going to just write this in terms of paths. You could keep track of it however you want, but just to give you the idea of the general way that you might be able to do this with breadth first search. So since breadth first search works in levels, like furthest away from the starting node, you kind of explore by level. So we're going to explore the first level, which is neighbors A, C, and E. So A has a distance of 12, C has a distance of 125, and E has a distance of 100. Then we basically keep track of those distances by updating some vector that stores the shortest distance. So A would now we now know we can get to A in a distance of 12 from G. We know we can get to C in a distance of 125 and E in a distance of 100. Then we basically keep popping off of our queue. So now we go to A. So from A, we know we can get to B. So B is the only neighbor of A that we can get to. So GAB can be gotten to in the distance we already went from G to A plus 115, which is the distance from A to B. So we can add that to the queue. GAB is 127, and then we can also update our distances array to know that we can now get to B from G in 127. You'll notice that we're doing this ordering based off of the ascending or alphabetical order of the neighbors. So now we're going to C because it's ACE as the neighbors. So GC is 125, and then from C we can go to D. That's the only place we can go. So GCD is going to be 125 plus 7, so that's going to be 132. So we can add that to our queue, GCD 132, and then we know we can get to D in 132. Now we're going to visit E, right? So we're going to pull GE off, visit E, and we can get there in 100. From E, we can go to C, D, G, and H. So let's assume, because we have the discovered set, that with breadth first search you don't revisit nodes that you've already visited. So we're going to not go back to C and not go back to D. That's how breadth first search works. So if what we have left is D, so D can be, we can get there in 130, and then H we can get there in 160, so 60 plus 100. So we'll add those to our queue. So we have GE, D in 130, and then we have GH, GEH. In 160. Update our distances. So D, we now can get to D in 130, and then H, we can get there in 160. So we keep on this general path, and eventually we're going to pull off a path that gets us to F, which is where we're looking to get, right? So we'll actually get there once we pull off GCD. Once we get to D, we can get to F, and that will be our path. And when we do that, we're going to find that BFS will give us G, C, D, F as our path, and that will be a distance of 159. So what happens with breadth first search is you get this idea that you can use these distances to find the shortest path, and it will always, breadth first search will find a path for you, but it has a hard time as is finding the shortest path because it doesn't revisit nodes. The shortest path is this path, and we miss this connection here because when we visited E, we don't go back to C in order to avoid cycles because we already went there. And so that's kind of the disadvantage of the breadth first search, is it can miss the shortest path. So we need to alter it. And so the idea that we're going to do to alter it is we're going to apply something called a greedy algorithm. So breadth first search is an algorithm that always visits the neighbors in sorted order, or whatever order the neighbors function sets them to. An alternative is to visit the neighbors in order of what would be shortest. So the way that we can do that is, instead of setting up a queue, we can set up a priority queue. And that's how the greedy algorithm portion of this algorithm works. So instead of visiting each one in terms of the order of the neighbors, we're going to visit in order of priority, which in this case is going to be the smallest weighted path first. So it's the same idea that we just did, but we're just changing it to a priority queue, and there's really not that much more to Dijkstra's algorithm than that. So we're going to again start with the starting node G and putting that into our priority queue and then pulling it off. So we pull off G and then we visit all of its neighbors. So again, it has A, C, and E as its neighbors. You can get to A in 12, you can get to C in 125, and you can get to E in 100. But the difference is when we put them into the queue, they're going to be now sorted by priority. I'm going to give this a little space because I'm going to insert stuff later. So GC, which is 125. So our priority queue keeps those in order, and so our distances down here are going to be the same: 12, 100, and 120. But what's going to happen is we are going to go ahead and visit the A first, or we're going to explore A first. So that's 12, and when we go to A, we know we can get to B in 15, so we can get to the whole thing in 127. We can get to B in 127. So when it gets inserted here, it's going to go back here to 127. So now we finished A. But then what's happening is that we're actually going to visit E before we visited C. Like in breadth first search, we went to C first. Now we're going to go to E first. And when we go to E first, E has lots of neighbors. It has G, it has C, it has D, and it has H, same as before. So we know that we can get to G and let's see, G we can get to in 180, C we can get to in 120, D we can get to in 130, and then H we can get to in 160, right? So we're going to go through and we're going to look to see if we found anything better. So with G, for example, that's not better than what's already here. We already can get to G in 0. C, same with C. Oh, I put that in wrong. So C is actually 125. Whoops. It's kind of a big problem. So actually this path here is 125 and I'd put in 120. So C, I actually just found a different path, 100 to from G to E to C. That's actually 120. So I found a better path. So I'm going to go ahead and put this new path GEC in because I found a better way to get to C than just going directly to C from G. And then what about D? So D, we saw we can get there in 130. So we're going to put the 130 in the queue. So that's going to be G. GED is going to be 130, and then what else do we have left? We have H. So H is going to be GEH. You can get there in 160, and we need to put that in there because we found something smaller. And we continue this process, and this basic idea, it allows us to find this path that we didn't have before. So now we're going to pull off GEC, and we know GEC is the path that we want, right? And you can see here how Dijkstra's is going to extract that for us because it's keeping track of this priority. And if we keep this process that I'm going through, which I'm going to do much slower and tracing it in a second, you can see that we actually get the shortest path, which turns out to be 154 using Dijkstra's that we missed using BFS. So the shortest path is GE, C, D, and then F. And if you add up all those paths, you're going to get 154. And the whole idea of it is the priority queue, right? It continues to check the distances, and if it's found a better distance than what it already has found, then it inserts that new path into the priority queue and it replaces the distance. So we're going to go through that slowly, but overall, you just keep walking through the graph, and every time you find a new distance, you're going to replace it. So we know that we can get to A in 12. We know we can get to E in 100. We know we can get to C in 120. We know we can get to B in 127. We know we can get to D in 127. We know we can get to F in 154. H 160. And this process, the algorithm goes through and it can find the shortest distance from V, starting V, to every other vertex in the graph. Or you can basically break out of the loop of Dijkstra's earlier if you just want to find the shortest path from G to a particular vertex. But in general, Dijkstra's can find the shortest path from start V to any other vertex in the node. And so let's go through what that actually looks like. The big thing is that it looks very similar to BFS, except for that it adds in this priority queue that allows us to search the smallest distance first. And then there's other edge cases that we'll kind of go over as well as we kind of walk through it. But the priority queue is the key here. I'm going to use the Zybook's version of Dijkstra's and trace that. You'll see here that there's some other additional things added into the Zybook's algorithm that are needed in order to actually make the algorithm functional. Also, some of it's added so that, you know, we can actually see that you applied Dijkstra's right by keeping track of a visited node, which we'll go over as well. This is needed in order to avoid revisiting nodes, and as well as breaking once you have once you've found the shortest path to all of them, which I'll show you in a second. So what we're going to do is go through this graph and show how this is created using the algorithm, using this trace that we've been using for the other algorithms as well. So we're just going to go through really carefully each of these iterations of the loop. So we're going to start by setting up our unvisited queue. So it's set up here. It's going to have the starting vertex in it with 0, as well as every other vertex in the graph with the initial distance of infinity. You're going to pop off the queue, the first element, which is going to be G in our case, and then we have this little clause here. So if the current V's distance is infinity, we're going to break, so it's not, because its current distance is 0. If it's already been visited, then we're going to basically skip this loop, otherwise we're going to visit it. So we haven't visited it, so we are going to visit it, and we'll keep track of what we visited here in this vector, which will just keep track of the order of the nodes that we visit. This isn't really necessary that you keep track of them in order, but it allows us to know that the Dijkstra's is right in the case of like auto grading and stuff, that you visited all of the nodes in the correct order. Then this loop is just going to find in all of its neighbors. So we've done this a couple times, so we know that G's neighbors is A, C, and E, and then we're going to go through and apply this code. So current V's distance is 0, and then we're going to calculate the edge weight for each neighbor and see if we need to update. So A's edge weight is 12, and so the alternative path distance will be 12. Basically, if that distance is shorter than what's already stored, it's going to replace it, and then it's also going to be added to the queue, which we'll do after we get all of them that we need to add to the queue so we can put them in order. C's is 125, so its alternative path distance is 125. 125 is smaller than infinity, so that it gets replaced. And then E's is 100, so with 100, 100 is smaller than infinity, so it gets inserted. So these are going to get inserted into the priority queue in order. So we're going to have A, E, and then C inserted, which is the same thing I showed you when I did it kind of quickly in the previous slide. But I will put C in correctly this time. And then we will always have every node inserted with the infinity. Then we have finished one iteration of this algorithm, and so now we're going to go to the next iteration. So now curve E is going to be A. So now our curve E distance is 12, and we're going to visit all of A's neighbors. So again, we haven't visited A, so we're going to add A to the visited vector. Now all of A's children are just B. B is 115, so we get 127. So to visit B, it is smaller than infinity, so we're going to go ahead and replace it and add it to the queue. There's only one on this case, so anytime we replace a distance, we add it to the queue. So B127 is going to get added to the queue. Okay, and then everything else in the distances array just carries through to the next iteration. So this is going to be 125, infinity, infinity. Okay, so now we're going to pop the next thing off the queue, which is E. E hasn't been visited yet, so we're going to visit it, and it's not infinity. So we go to all of E's neighbors. So now we're at E. E has a lot of neighbors. E has C, D, G, and H as its neighbors. C, D, G, and H are all the neighbors that we're visiting. So the current distance that we're dealing with is 100. And so now we need to go through and look at each of the neighbors and see if we need to consider those paths. So let's start with C. C is 120. So if we look here, 120 is smaller than 125, so we're going to want to consider that one. Now we'll go to D. D is 30. So 130 is less than infinity, so we'll need to consider that one. Then we will go to G. G is 180, but we can see that G's minimum is 0, so we're not going to add G. And then H is 60, which is 160 is less than infinity, so we're going to want to consider those. So we're going to have to insert all of these into the queue. The smallest one is C, so that will go in to the front of the queue. Then we have another C with 125. We have D, which is 130. Oops, but B is smaller, so it's going to be B 127 and then D 130. Then H 160. And then we'll have infinity. Just make sure I have this right before I move on. Okay, everything else is just going to carry through to the next iteration because we didn't change any of those. Now we pop off C, and we have a current distance of 120. So now we're going to be at C. C only has one neighbor, which is D. So we're going to add D here. We're also going to visit C. Because we hadn't yet. D is 7 away, so we're going to go to 134 as the alternative distance. But if we go here, we can see that C has a distance of 120. So we didn't find something smaller, so we're not going to add anything to the array, or add anything to the priority queue, because we already have a shorter path. Oh, I did that wrong. Just let me take a step back. So the path that we have just found is from C is, okay, I think I really messed that up actually. Let's start over. So we're at C. C's path weight is 120. So we have 120 here. And then we know to get to D, it's 7. So that's 127. So we're going to go to D here, and that's 130, so we did find a smaller path, 127, so we are going to need to add that to the queue. So now we have C125, we have B127, and then we'll add D127 after. This is a tie, so depending on how your priority queue is set up, as you all know, that will depend on how this tie would be handled. So now this is our priority queue. All right, everything else is just going to carry over here. All right, now we're going to pull off C. So here's a case where we need to think more about this condition here. So this isn't true because C's distance is not infinity. C's distance is 120. But current V has been visited. So since we already visited C, we apply the continue statement, which is going to skip the loop and go on to the next iteration of the loop. In the next iteration of the loop, we're going to go to B. So B we haven't visited, and it's not infinity, so we're going to go ahead and visit it. When we go to B, we only have one neighbor, which is D. So let me apply this. I'm just going to apply that. Okay. So B is currently at 127. And the edge weight to D is 1. So we're at an alternative path distance of 128. So if we go to D, the distance 127 is actually smaller than 128, so this one doesn't replace anything, so nothing gets added to the queue. So I'm going to rewrite the queue down here as it stands, because we were pulling things off of it, but we haven't added anything to it on the last two iterations. And then the distances array also doesn't change because we didn't find anything new to replace anything. All right, so now we're going to pull D off. So D is also a distance of 127. And let's see who we can visit from D. We can visit H. And we can visit F. So let's try both of those. So let's start with F. D to F is 27, so that's an alternative path of 154 for F. F is currently at an infinity, so we found a shorter path, and so we're going to add that to the priority queue. And then we're also going to visit H, which is 37. So that's going to be 164 as an alternative distance path, but we already have a shorter distance to H of 160, so we are not going to replace that. But we do need to add 154 F to our priority queue. So we'll do that. So we have 130, we have F 154, and then we have H 160. And then we don't update any other distances because we didn't find any more information to add. All right, we're going to visit D. Oh, and we visited D on the last one. So D, we already visited D, so we're going to hit into this branch of the if statement up there, which means that it will skip this iteration, so everything will just carry through. So the distances array doesn't change at all because nothing runs for this iteration because of the continue statement. And then we're going to pull off one more thing here. So we have F. So now we are visiting F. This is our first time we're visiting F, so we're going to add it to the visited queue. And or here. So let's see, where does F link back to? F goes to D and F goes to H. F's distance is 154. And then to go to D, it's 27. So we already have a much faster way to get to D. We have 127, so we don't even need to do that calculation, so we can skip that. But then let's try H. So we're at 154 with F, and then we can get to H in 20, so that's 164. But you can see we can already get to H in 160, so we don't have to replace that either. So nothing gets added to the Q, so our Q is just going to be left at 160, and then all the infinities are going to be in here still. And then our distances array is not going to change. We do have one more thing to pull off the Q, which is H. And H we haven't visited yet, so we will visit. H doesn't have any neighbors, as you can see, and so it has nothing to visit, so nothing's going to change. And then finally we will pop off A with infinity, and we'll get to this statement here that the distance is infinity, so that means that we break out of the loop and we're done. And this is our final distances array, which Dijkstra's has calculated the shortest distance from our starting vertex, which in our case was G, to every other vertex in the graph. And that's how the algorithm works in full detail. So I hope that helps you understand how Dijkstra's algorithm works, and that is it.